Hi, I'm Subhashini, and I'll be presenting our work on developing speech recognition models using large language models and adapting them to disordered speech using reinforcement learning. The motivation for this comes from a Google project called Euphonia to help improve speech recognition for individuals with speech disorders. We created an app called Project Relate that allows individuals with speech impairments personalize their own on-device model so that they can be better understood. In all of these cases, we can ask if providing multimodal context, such as images along with the speech, would help improve recognition. So we're thinking if like multimodal large language models can help recognize impaired speech. But perhaps trying to do it even with text only large language models might be a good starting point, since large language models already have a lot of world knowledge. So the first question we ask is, can we add speech inputs to the large language model? And if this can And if we made this on small open source models, we could potentially run them on device. So how do we turn a large language model into a speech recognition model? We need to tokenize the audio similar to how text is tokenized to build a vocabulary. To do this, we use an existing audio tokenizer and cluster embeddings to create our audio tokens based on the centers of the clusters. We then map the cluster centers to the vocabulary of the large language model. Specifically, we replace the low frequency tokens in the LLM vocab and repurpose them to be the audio tokens corresponding to the cluster centers obtained from the audio embeddings. In this case, we do this on the Libri speech corpus. Then, this model, when fine tuned on the Libri speech dataset, becomes a speech recognition model. We first train the model on Libri speech, and then it's also adapted to disordered speech by tuning it on about 1,000 hours of disordered speech data from Project Euphonia. When we do supervised fine tuning, it's not enough to train on Libri speech alone. So, what you see on the top right is the loss curves, and the green curve indicates that performance of generalization is low and it doesn't generalize well to the disordered speech. So we use a mixture of standard Libri speech along with the disordered speech data to fine-tune the model. Specifically, a 30-70 mixture does even better, which is the orange curve. And on held out evaluation datasets, we see that the model is able to have a low word error rate on both Libri speech and generalize better to disordered speech. MP stands for meaning preservation here, which I'll come to in a little bit. So the next question we ask is if reinforcement learning can help generalize further than standard supervised fine-tuning on the disordered speech data. For reinforcement learning, we need some sort of a reward. To do this, we examine if we can get a reward from evaluation on semantic meaning preservation of the ASR output. So we can reward the model if the meaning is closer to the actual transcript, even if it is inexact. Here's an example of how we can use a reward model. For example, if the ground truth is not so good today, transcript B preserves meaning, whereas transcript A, which is saying not so good to the, doesn't preserve meaning. Specifically, even when the word error rate is high, meaning can still be preserved. And in this case, both options A and B have the same word error rate, but B preserves meaning better. In our work from ICASSP 2024, we show how large language models can be used to build such a reward model, specifically for meaning preservation. Specifically, what we did was we trained large language models to predict human labels on whether meaning is preserved. Our best performing model achieved an AUC of close to zero point 0.9. In this work, we retrain a smaller large language model, specifically the Gemma 2B model, again as a reward model, and we achieve an AUC of nearly 0.88. We can then combine the meaning preservation and word error rate to provide a reward signal for reinforcement learning. Here we show a weighted way of combining both the reward from meaning preservation and word error rate. Specifically, we use these rewards to align the model. We check with different settings where the reward comes from just word error rate alone or different weights on the word error rate and meaning preservation, where gamma is varied. Our first key observation is that using meaning preservation as a reward shows significant score improvements on the meaning preservation metric as expected. So, RL on this data and reward appears to work well. Further, we see that there's a substantial improvement in meaning preservation, while the decline in word error rate is not as significant. When we slice the test data by the severity of the speech disorder, we see more pronounced improvements in speakers with more severe disordered speech, which is the green bar here on the right. Based on human evaluation on the test set, we find that there's significant improvements in the RLHF model performance, and there's also a significant correlation between human judgments of meaning preservation and the reward model scores. Here are some examples of ground truth sentences and the sentences generated with word error rate alone as a reward and the combination of word error rate and meaning preservation as reward. So, for instance, if the ground truth was everyone of my family listens to music, with word error rate alone as a reward, it says everyone's in my frame and listen to music. Whereas with both the meaning preservation and word error rate as reward, we can see that it kind of gets a much better transcription, which says everybody in my family listens to music. So, although there are some errors, it preserves meaning much better. In summary, large language models can be modified to recognize speech, and supervised fine tuning on a mix of standard and disordered speech datasets help. We also find that reinforcement learning can help further generalize the model to disordered speech, and meaning preservation and word error rate can be combined to provide a strong reward signal. Thank you.